Okay, instructions are clear. Okay, so question number 1, which is the multiple choice questions, they're telling us 4 options are provided as possible answers to the following questions. Which question has just one correct answer? We need to write the letters next to the question number. Okay, so 1.1, they're telling us that an object that is negatively charged. An object is negatively charged if it has more. So one thing we know about charged bodies is that as long as any object will have what we call the nucleus, which nucleus will be made up of the protons and the neutrons. And then we shall have electrons just around the body. Now, if we have excessive electrons, then the body will tend to be negatively charged because the net charge is going to be negative. And if the body tends to have more protons compared to the electrons, then the net charge will be positive. So in this case, since the body is negatively charged, which means we expect the electrons to be more than the protons. So we're going to have this. Then 1.2, they're telling us that we have 3 identical balloons, each carrying a charge, and they are suspended from a ceiling, as shown in the diagram below. Okay, balloon S is negatively charged, which means there's a negative charge here. One thing we know about the properties of charges is that unlike charges attract each other, and then like charges do repel. So if this is a negative and we are seeing attraction between R and S, which means R has to be a positive. And there's a repulsion between S and T, which means T is negative. Okay, which combination is correct with regards to the charges on the balloons? So we're saying that R is positive, S is negative, T is negative. I think the only option is option A. Then 1.3. Opposition to the flow of electric charge. Opposition to flow of electric charge. It cannot be EMF. It is resistance. Then 1.4. Consider the circuit diagram below. Okay, so which of the following ammeter readings is correct? Okay, so what we said was that for as long as resistors are in parallel, the current is going to be split up. So this is I2, and then probably the current passing here is I3. For us to get I1, it will be a combination of I2 plus I3. So let's see the combinations that have been given. They're telling us that A1 is the same as A2. That is wrong. The current entering A2 is smaller than A1. A1 is twice A2 plus A2. Nope. That would have been correct if this resistor was also 2 ohm. A1 is a third of A2. That is wrong. A1 is the same as A2 plus A3. That is correct. And then they are telling us that A2 is greater than A3, which is also correct because the resistance here is 2 ohms. And the lower the resistance, the higher the amount of current that is flowing through that component or resistor. So option B will be the correct answer. And now we move on to question 1.5. They're telling us that the amplitude of the sound wave is increased without changing the frequency. So this thing is even in bold, even this one. Okay, so how does that change, or how does that affect the loudness and the pitch? So we need to know what is amplitude. We know that this is the maximum displacement. And maximum displacement is directly proportional to the loudness. That's number one. So which means if the amplitude increases, even the loudness must increase. Okay, so from these options, we're already looking at C, and then we're looking at D. When I look at pitch, pitch has nothing to do with amplitude. The pitch is just related to the frequency. Okay, so now, if the frequency is constant, which means even the pitch has to stay the same. So I'll go with option D. Then 1.6, are telling us that consider the diagram of two processes shown below. Okay, we're having an amplitude of 30 centimeters, amplitude of 20. The motion is in the opposite directions. Okay, so when these two waves meet at X, what's going to happen when the two pulses diagram meet at point X? The type of interference. Okay, so one thing we know about interference is that for as long as the waves are moving the same direction, then there's going to be superposition or constructive interference. But for as long as they're moving in opposite directions, then there's going to be destructive interference. Okay. Now with the destruction, since this is a 30 moving to the right, and then this is a 20 moving to the left, when the two combine, it's going to be a destructive interference, looking at A and B, but then what will be the resultant amplitude? It's going to be a 10. Okay. In other words, the amplitude of the resultant must decrease. Then 1.7, consider the following statements regarding gamma rays. Okay. They have higher penetrating ability than X-rays, which is true because the gamma rays have a higher frequency. Okay. When they travel at 3 times 10 to the 8, that is also true since it is part of the electromagnetic spectrum or electromagnetic waves. Then lastly, they have longer wavelength than microwaves. This is wrong because we know that gamma rays have a shorter wavelength compared to the microwaves. So which one of the following combinations is correct? So I'll go with A, that is showing me just 1 and 2 only. So guys, that was question number 1. Let's look at question number 2. They're telling us a circuit diagram below, or circuit diagram shows a circuit consisting of battery of negligible resistance. We have 2 ammeters also whose resistance can be ignored. Then we have 3 resistors and 2 high resistance voltmeters. Okay, what is relevant is that A1, reading of A1 is 1 amp. Okay, so the current here is 1 amp for the 6 ohm resistor. All right, then question 2.1, can we define what electric current is? Okay, so we're saying that electric current okay, complete the following sentence by filling in the missing words. Resistors in series. What happens to resistors in series? What do they divide? And what happens to resistors in parallel? What do they divide? So one thing we know about resistors in parallel is that the voltage will be the same. The voltage is maintained, it's a constant. But the current is being split. In other words, the current that is passing through 6 ohm is not the same current that is passing through the 12 ohm. So we say this divides the current. And then if resistors are in series, they divide the voltage, or we can call it a potential difference. So 2.2.1, we're going to call potential difference. Okay, potential difference, or sometimes we call it PD. And some people can even call it a voltage, no problem. And then 2.2.2 is saying the current will be divided. All right, then 2.3, they want us to get the effective resistance of the parallel combination. Now, one thing we need to remember is that as long as we have a parallel combination, okay, so I'm looking at the 6 ohm and then the 12 ohm resistor. As long as it is just the combination of two resistors, it's a quicker way. But let's start with what people are familiar with. So we said 1 over R will be 1 over R1 plus 1 over R2, which is 1 over 6 plus 1 over 12. You can decide to find the LCM or the LCD here. That will be 12, okay, which means I have 2 plus 1 of 12, which is 3 over 2. And then I'll cross multiply, which means my R is going to be 12 over 3, which is a 4 ohm. Okay, so that would be the effective resistance. What I usually prefer using is that for as long as I have two resistors that are in parallel, my effective resistance would be the same as the product. Okay, I can just get the product of the two resistors divided by the sum of the two resistors. So my product would be 12 times 6 divided by 12 plus 6. So that is a 72 over 18, which gives me 4 ohms. So whichever format you use, you'll get the same answer. Okay, that is 2.3.1. Then 2.3.2, they want us to calculate the total resistance within the circuit. Now, what we need to know is that now the 4 ohms that we have is like one block of a resistor that is representing these two. Okay, so this block is going to be in series with the 18 ohm. And we know that when we are getting the total resistance in a series, we just add up. Okay, so it's going to be the 4 ohms plus the 18 ohms, which gives me 22 ohms. All right, then 2.3.3, they want the amount of charge that is passing through A2. Where is A2? So A2 will be the total current of the circuit. Now, since we got the effective resistance as 22 ohms, are we in position to get the current that is passing here? Do we know the voltage? So those are the questions we need to ask ourselves. So what I'm going to do, since I know the current that is passing through the 6 ohm, I can use Ohm's law or Ohm's formula. Okay, this is 2.3.3. Okay, so I'm gonna say that from V is equal to IR. My voltage is gonna be the current, which is the 1 ohm, times the resistance, which is, 1 ampere times 6 ohms, which means I'm getting 6 volts. Now, what we said was that the voltage across a parallel combination is the same. So it's the same voltage that is passing through the 12 ohm, and it's the same voltage of the entire circuit. So what I can do, I can use this 22 as my resistance, and I can use that voltage. Okay, so I can say that the current that is passing through A2 would be I is equal to V over R. Okay. Does that make sense though? Is that gonna make sense for me? Let's see. Because my voltage is that, my effective resistance is that, which is not gonna make sense. Let me just find the current that is passing through the 12 ohm. Okay. So current through the 12 ohm resistor. Okay, so my voltage is 6 over the resistance, which is 12. Okay, so I know that 6 over 12, 6 divided by 12 must give me 0.5. Is that true? We're saying 6 divided by 12 is 0.5, yes. So which means that the current through this is 0.5. And if this 0.5 comes through this, and the one also comes through that, it will be a combination. So that my current I on A2 is going to be 1 plus 0.5, and that's going to give me 1.5 amps. Okay, so we say the voltage, this 6 volts, is just across this parallel combination, which is different from the voltage across the 18 ohms, since there is a series combination afterwards. We haven't answered the question. The question is asking for the charge. Is that true? Yes, the amount of charge. So from our formula sheet, we know that charge is obtained by getting the current times the time. Okay, our current is 1.5. The time, we're talking about 5 seconds. Okay, so 1.5 times 5, I'm ending up with 7.5 coulombs. So that's how one would have claimed the 5 marks. Okay, then 2.4. 2.4, they're telling us that how does the potential difference across the 6 ohm compare to the potential difference across the 12 ohm? Remember, it's the same parallel combination. And what did we say? That the parallel combination only splits the current, but the potential difference stays the same. So we're gonna say it's equal to. Okay, what would be the reason? The reason could be that in a parallel combination, or we can say a parallel combination, or we are saying a parallel combination of resistors is a current divider, and the PD stays the same. Across the resistors, or something like that. And then 2.5, they're telling us if the 6 ohm burns out. Okay, so if this is out, no longer there. So which means the current will have just one route to flow through. So there, and then it will take this route. So which makes the 18 ohms and the 12 ohms to be in series. Okay, so our effective resistance in that case will be 18 plus 12, which is going to be 30 ohms. Now they're asking us, will the total resistance of the circuit increase or decrease? Now you can see that this 30 is way bigger than the 22. So the answer is just going to be increase. That is 2.5. Then question 3. Question number 3. Okay, they're telling us that a group of learners conduct an experiment to determine the charge on each of the 4 objects. We have M, N, R, and S. So they use an object X that is having a negative charge. Whereas, okay, so we're saying a group of learners conduct an experiment to determine the change on the charge on each of the 4 objects. We have M, N, R, and S. So they used an object X that's having a negative charge. as well as a neutral object P. And then the following we observed. Okay, so I don't know where to start from. Okay, so if X is having a negative charge, so which particle is having the first interaction with X? Okay, so we have S here. So S attracts X. So which means if X is negative, I don't know, let me just put it here. Okay, which means S, for as long as they attract each other, which means the signs are opposite. S is going to be positive. Okay. Then the interaction between S and each other one, so S is being repelled by some other object and it's okay. They're telling us R attracts N, but repels S. Okay, so if S is positive, which means R is also going to be positive since there's a repulsion. But R is attracting N, which means N is going to be a negative. Opposite signs must attract opposite charges. Okay, then if that is true, we still have R that is repelling M. Okay, R repels M. But we said R is positive, so which means M must also be positive. All right, I think that is that. What do they want? They want the symbol, write the symbol on the spheres M, N, R, S. Then next to the symbol, you must write positive or negative. Okay. So when you look at, I'll say M, it's going to be positive. And then when I look at, you said MN. When I look at N, you said it's negative. Okay. And then we have R. What did we say about R? R was positive. Okay, so that is positive. And then lastly, S, we concluded that S was a positive. Okay, so that is positive. So we only have one negative sphere there with all that we've been given. All right, so if that is true, then we move on to 3.2. 3.2, they are asking us that, they're telling us that two small spheres, G and H, on insulated stands, they carry charges of this and that respectively. Okay. So we have negative 2 times 10, negative 9 coulombs, then negative 6 times negative 9 coulombs. Then 3.2.1, they're asking us, how does the number of electrons in G compare with the number of protons on G? Okay, we must choose from the following: less than, the same, or more than. Okay, so now since the net charge on this sphere G is negative, which means we're going to have more electrons. Okay, so my choice is going to be more than. And then what's going to be the reason for the answer? We're saying that the net charge on G is negative. Hence, we have more what? We have more electrons than the protons. Then state the principle of charge quantization. Charge quantization. Okay, so this principle simply tells us that a charged particle, charged particle can do what? Can have a charge, can have a charge that is equal to some, or we can say equal to, let's say, an integral number. equal to an integral number. In other words, they want you to explain what this Q is equal to NE represents, because that is charge quantization. Okay, then 3.2.4. Now they're asking us to calculate the number of electrons on H. So 3.2.4, we're gonna say that Q is equal to NE. But for us to get the number of electrons, it's N, which is Q over A. Okay, from the formula sheet, you can find that from the formula page. Okay, so we know that the charge on H, is -6 times 10 to the -9. Okay, so that's gonna be -6 times 10 to the -9 coulombs. I'm dividing this by the charge of an electron, okay, by electron charge, so which is -1,6 times 10 to the -19. Okay, and then when I simplify that using my calculator, what are we getting? What are we getting? So it's saying -6 times 10 to the -9 over -1,6 times 10 to the -19. Okay, so I end up with 3,75 times 10 to the 10 electrons. So that's how much electrons we have. All right, then the spheres are allowed to touch, okay, and after which they are separated again and return to their original positions. Now state the principle of conservation of charge. So we can say that in an isolated system, okay, the net charge is conserved, or the net charge of the system will be conserved, which means if we don't have any extra charge, any extra interaction, the charge must always be the same, must remain the same. Then 3.2.6, they're telling us during contact, the electrons were transferred from sphere H to G. Calculate the number of electrons that were transferred to G. Now, one thing we need to remember is that for as long as these spheres are allowed to touch each other, there's going to be flow of charge between the two, okay? And when they are separated, the two spheres must have the same magnitude after the separation. So we need to first of all determine how much each of the spheres will have after the separation. So for us to do that, we must get the average charge. So that's gonna be, we're saying this is 3.2.6. It's gonna be -2 times 10 to the -9 plus -6 times 10 to the -9. And then I'm dividing this by 2. Okay. When I punch that into my calculator, I'm having -4 times 10 to the -9 coulombs. So this will be the new charge on each of the spheres, okay? Then for us to get the charge transferred, okay, charge transferred, we're just gonna get, let's say -4 times 10 to the -9 minus -2 times 10 to the -9. So I'm doing this with reference to the charge on G. Okay, since they want us to get the number of electrons transferred to G, so I can use the charge of G. Okay, when I simplify that, I'm getting -2 times 10 to the -9 coulombs. Then from my N is equal to Q over E, I'll get the -2 times 10 to the -9 over -1,6 times 10 to the -19. When I punch that into the calculator, I'm gonna get 1,25 times 10 to the exponent of 10 electrons. Okay, so we're using this because this is the amount of charge that was transferred. So from this charge that was transferred, how many electrons do we have there? So this is how much electrons we have in that case. All right. Then we move on. Move on. That is question number 3. Question number 4. Question number 4, they are telling us that electromagnetic radiation has a wave particle duality. What does this mean? So in other words, the radiation has two tendencies, or it exhibits two tendencies. What are those? So we're gonna say that waves, the waves do exhibit what we call the particle-like properties. Okay, in other words, these waves behave like particles. And then the particles also, while the particles can also behave, or they can exhibit the wave-like properties. The wave-like properties. So we know that electromagnetic radiation is made up of particles, and this electromagnetic radiation can also be in the form of a wave. So waves exhibit particle-like properties, and then particles can also exhibit wave-like properties. So that is the particle duality. Then they want us to arrange the following types of electromagnetic radiation in order of decreasing wavelength. So when we talk of decreasing wavelength, it could be the same as increasing frequency, because you know that wavelength and frequency are inversely proportional. So all I know is that the electromagnetic radiation with the highest frequency is gonna be number 1. Okay. Then I'll have the X-ray. Okay, and then from there, I'm gonna have number 3 as the visible light, and then number 4 is going to be the infrared. Okay. Okay, so my answer is gonna be the gamma rays, number 1. Number 2, I'm gonna have my X-rays. Number 3, I'm gonna have my visible light. And then lastly, I'll have my infrared. Then 4.3, they want us to define what a photon is. Okay, so a photon is just a packet of light particles. Okay, we can say it's a packet of what we call light particles. A packet of light particles, or someone can say these are particles or bundles of electromagnetic radiation. Electromagnetic radiation. So it's either this or it's all right, no problem. Then 4.4. 4.4, they're telling us that an electromagnetic wave has a wavelength. So my lambda is gonna be 2.5 times 10 to the negative 9 meters. Can we calculate the amount of energy that a photon of this wave has? So from our formula of E is equal to HF, we know that E is representing the energy. We know what Planck's constant is. We don't have frequency, we only have the wavelength. Okay, but from C is equal to F lambda. Oh, there is another formula anyway. So we can say that lambda is the same as C over F. What's wrong with me? What am I making the subject? I have lambda, so I have to change the frequency, make the frequency the subject. So frequency is C over lambda, which means I'm gonna use E is equal to H times C over lambda. Okay, we can get H from the back page with the information. So H is gonna be 6,63 times 10 to the negative 34. Our C is the speed of light, which is 3 times 10 to the 8. I'm dividing by my wavelength, which is 2,5 times 10 to the negative 9. Okay, so when I punch that into my machine, which is my calculator, why doing this to me? Okay, so it's saying 6,63 times 10 to the negative 34, multiplying it by 3 times 10 to the 8 over 2 times over 2,5 times 10 to the negative 9. So I'm having 7,956 times 10 to the negative 17, but this will be joules. All right, so that is that. And that is how we would have worked out 4.4. All right, we move on to the next question. Question number 5, telling us that the diagram below represents a wave that is moving from left to right. Okay, the wave is moving at a speed of 0,4 meters per second. So my V is 0,4 meters per second. Then we have frequency of 0,5 hertz. All right, so what we can see, seeing some properties, the amplitude, we have the wavelength, and then yeah, all right. 5.1, can we write down the amplitude of the wave in meters? Now we know that amplitude is the maximum displacement. So from the rest position, which is 0, how high is this wave going? It's reaching 40 centimeters. Same thing at the bottom from here is negative 40. Now, how do we convert 40 centimeters to meters? 40 divided by 100, and then we have 0,4 meters. Then 5.2, can we label or can we name the points D and E? So from this, we know that D is what we call the trough. Okay. And then our E is what we call the crest. The topmost part or the turning point of the wave is the crest and then the trough. So the maximum is the crest and then the minimum is the trough. So we say D is the trough and then E becomes the crest. And then 5.3, they want us to define what is meant by wavelength. Okay, we know that wavelength, look at this. If we look at from this point up to this point, that will be like one wavelength. Okay, so the distance between one full cycle of a wave or between two successive points and things like that. So I'm gonna name or label it or define it as the distance that is between points. Okay, on a wave for just one cycle. Okay, for just one cycle. Someone could also talk about the points between adjacent crests or adjacent cycles of a waveform, whichever way you put it. Then 5.4, can we write down the points on the wave that are in phase? So to be in phase simply means the waves must be more or less at the same level. Okay, so we can look at A and B now. Yeah, it could be A, B in the same phase. Someone can also say A and C. are also in the same phase, so B and C are in the same phase. So I'm gonna take A and C in this case. Okay, so 2 points, I'm gonna say A and C are in the same phase. Okay, because both points are on this other part of the wave, the decreasing part of it. Then how many waves are represented in the diagram? So remember what we said, that from this point up to this point, this is gonna be like one full wave. That's one cycle. And then from here, a combination of the trough and the crest, that's also another cycle. So that is wave number 2. And then from here to here, it's just a crest, which is gonna be a half of the wave. All right, so what we can say, this is 1, 2.5. So we're gonna say we have 2.5 waves. Okay, someone can write it as 2.5, 2 whole numbers and then 1/2. Then calculate the wavelength, the lambda. How do we get that? How do we get that? So we were given some information from the top. Okay, we have the V, we have the F. So from that formula that talks about V is equal to F lambda or C is equal to F lambda, they want a lambda, which is the wavelength, which means we must get our velocity divided by the frequency. Okay, the velocity they gave us was 0.4, and that is 0.5. So I'm gonna have 0.4 divided by 0.5. Okay, I'll punch that into my calculator, and then I'm getting 0.8. Okay, 0.8, but since it's wavelength, I'm gonna call it meters. Then 5.7 determine the distance D as shown in the diagram. So in other words, the distance from the start up to the end. So if this distance is 1 wave, and then 2 waves and 2.5, but 1 wavelength we say is a representation of 0.8, then that's gonna be also 0.8, and then that's gonna be probably 0.4. Okay, so we want just that distance. So what one can do, you can just get the 0.8 times the number of waves, which is 2.5, and that gives you 2 meters. Alternatively, someone can look at velocity being the change in displacement over the change in time, or speed is distance over time. We're looking for the distance. So it's gonna be the velocity times the time. Our velocity, they told us, was 0.5. Is that true? Was it 0.5 or 0.4? It was 0.4. The velocity was 0.4. Okay.